What we have looked so far in reliability prediction models and methods, the methods like two models, exponential distribution and Weibull distributions, are used to model the reliability of individual components. But in day-to-day life, we always use systems. A car is a system, it's not an individual item. Even though individual item can be like bearings, etc. But in general, most of the items and assets we are using are systems like a track system or a rolling stocks in railway, your mine trucks, etc. So now I'm going to demonstrate and describe a couple of very simple methods. How can you evaluate the reliability of systems? Now we are going to look into some of the methods used by engineers to evaluate the system reliability. Prior to that, let us see what is the meaning of system. System is a collection of components or subsystems assembled to perform a specific task. So many items, components should function together to deliver the function, and that's a system. And also we should remember, reliability of a system is determined during the design phase. Means design engineers have a lot more responsibility to inbuild reliability into the system. And sometimes that is referred to as design reliability. For calculating system reliability, we need to know reliability of individual components. If you want to know what is the reliability of particular system, you have to have information about components constituting the systems and their reliability, and also their configuration, how they are connected to each other, how their function, individual function will impact the system functionality, etc. In practice, three methods are popularly used. One is called reliability block diagram methods, and it consists of series configuration, like based on the when system subsystems or the components are connected in series, it is called series configuration or series system. When components are connected in parallel, they are called parallel system or parallel configuration. And when it is a mixture of series and parallel, it is called mixed configuration. Then also other methods are failure mode and effect analysis, that is used in design, and also fault tree analysis used in design, and or investigation of breakdowns, etc. Let us look into the reliability block diagram and series configuration. In a series systems, all components or subsystems must function for the system success, like a functionality of the system. When I want that my system should deliver the required function and all system components must work. Like let's say this is an example of a system. There are 4 components and each component should work. If let's say component 2 is not working, then system will fail. That's the key. So series system reliability, the reliability of such system is given by simple expression like R1, that reliability of component 1 multiplied by reliability of component 2 multiplied by reliability of component 3 multiplied by reliability of component 4. So general equation is of a series system is like a R1 dot R2 dot Rn, like a n number of components. Series system reliability will be, if you look, will be always less than or equal to the component reliability with the lowest value, because it's a product rule. If let's say we are considering a component, 2 component series system, and each one is having 0.5 reliability, so system reliability will be 0.5 multiplied by 0.5. It's like a 0.25. It's much lower than the individual component reliability. For high system reliability, it is important for all components to have high reliability values, especially when the system has a large number of components. So as the number of component increases, reliability value will be decreasing. System will become less and less reliable. Let's look into this simple example. This is a x-axis is the individual component reliability, 0.98 to 0.95 to 1, and y-axis is series system reliability of the system. One is at the top. Let's say a component with one component, and individual reliability is 0.8, And you'd see there is not much difference. Even if I want to achieve 1, it can be easily very little if one component, so same value will get. Is one component, one individual reliability, it will be same value will get. But what happens with the 10? If 10 components each having 0.98 reliability, it will be very less. It will start at almost near 80%, even though the individual reliability is 0.98. To achieve 1, each one has to have 1 reliability value. Similarly, you see for 25, you'll see as the number is increasing, reliability value is decreasing dramatically. If you have 100 components in a system, they are connected in series, each one is having 0.98, the system reliability will be much lower than even maybe 0.19% only. And what will happen if you have 200 components? It comes down to just maybe 5, not even or even 5-6%. And with 400, it's almost nearing to the 0, even though individual system reliability is 98%. So this is a demonstration. As number increases, reliability drops dramatically. If you want to increase the reliability, you have to have very high reliability, almost 100%, so that you can get the high reliability of 100. Okay, so series configuration summary. The reliability of a series system can be improved by increasing the component reliability by redesign. So you have to redesign the system. Means like you have to find a way to increase the reliability, or you can also by removing or decreasing the number of components also you can improve the system reliability. So there are different way of playing around with this design part. And next we'll be looking into the parallel configuration. That's one way to increase the reliability of the components, etc. So reliability of the system, I mean. Now let's look parallel configuration. In parallel configuration, all components must fail for the system to fail. So even one component is working, system will be functioning, and reliability will be at least given by the component with the largest reliability value. And reliability of a parallel system is given by 1 minus R1T multiplied by 1 minus R2T, that is the reliability of the second component, multiplied by 1 minus R3T. And if you have an n component, you can have 1 minus R1T. So idea here, if you remember, 1 minus R1T is nothing but a failure probability, cumulative failure probability. And so cumulative failure probability multiplied by cumulative failure probability of multiplied by component 2 to the component 3 and 1 minus, so you get the same value. So they are very closely related to series. It becomes like a series here, therefore in case of failure cumulative probability system we are calculating. And third one is called sometime, let's look back here, it's called also parallel system is grouped into two groups. One is called cold parallel and warm parallel. Warm parallel, what we have looked into the configuration. Cold parallel means components are not working all the time and they are standby. And this is the practical case, it is the most useful things. Like in a mine, if I am using 2 crushers, both crushers are not working. Only one crusher is working and second crusher is used as a standby. When first crusher fails, we restart the second crusher. And that is like you have to switch on manually, as against in parallel every component is working. So in a warm parallel, it is used in electronics where there is no wear and tear, whereas in a standby configuration, also cold parallel, it is used in the mechanical systems. Such applications like in aviation, jet engines, braking systems, projector light bulbs, like if I'm presenting something, light bulbs goes, it creates problem. So often people are using light bulbs in parallel. Both the bulbs are working. You don't notice it. And a parallel summary, parallel system works as long as one of the component works. Also, parallel system is used in design very often to increase the reliability of the components. because it is often it is a fast solution and you don't need to develop new technology for that. But cost, the negative part is the cost increases, and it might not increase the reliability very much unless it is done very properly. So parallel configuration is very important, very useful to improve the system reliability, but it costs a little bit more. But maybe due to the restriction of state-of-the-art technology, we don't have right type of material, we don't have right type of technology to increase the system reliability, then parallel configuration is the only way out, parallel configuration design. So this is very important. But in reality, we don't have system that is series, we don't have system that is only parallel. Often we have a mixed system configuration, which looks like that, like component 1 and 2 are in parallel, and these two jointly connected to component 3 and 4, which are also in parallel. So we have to solve this. If you want to solve this solution, you have to calculate the reliability of this in parallel using the parallel model, parallel way of approach, and this, and then again use the series configuration and series model to calculate the reliability of this system. You will be working some of the example on this, and you will understand how this works in practical. Again, I am repeating, this idea is just to demonstrate how these things are done in practice, but we use a lot more complex methods and numbers, etc. in practice. Now we'll be looking into two more these methods. I said failure mode and effect analysis. This is one of the most common method used by design engineers. So FMECA is the most widely used reliability analysis techniques and was developed in 50s to study the military systems. As you know, the history of reliability started in 50s, and FMEA was one of the methods. Failure mode effect analysis involves analyzing a system in terms of subsystems, assemblies, and so on, down to the component level. So you start analyzing the system as a whole, go down into, you try to partition the system into different parts and come down to the component level to identify individual failure modes, causes, and its effect on the system performance. And failure mode effect analysis becomes failure mode effect analysis, effect and criticality analysis if criticality is assigned to failure mode effects. So certain failure mode have very critical values, and if you are calculating those numbers, that analysis is called FMECA, failure mode effect and criticality analysis. And this is also very commonly used terms in design, review and design. Failure mode effect is a inductive methods, like you go by induction logic of analysis, where one starts with failure event at component level and then proceeds towards the system level to evaluate the effect of failures at system performance. So you start looking at the component level, what happens if this component is failed and how it will impact the performance. The driving principle in this analysis is bottom up. As you see, I say all the time, I'm saying start from the bottom, and you ask the question, what happens if, and is commonly used in design of systems. This is the methods FMEA. One example, this is from the Nova Air training materials. Coffee maker functions. What are the function of a coffee maker? I'm just giving you how to FMEA is used. Failure mode effect and criticality analysis is used. Like function is to brew the coffee, maintain the coffee at 80 degree to plus minus 5. Contain coffee in the pot, it should not spill here and there. Brew coffee at not less than 1 cup per minute, there is rate, the demand on the capacity. Automatically brew coffee at time as specified by the users, you can program it. Automatically shut down coffee makers 4 hours after brew cycle is completed, or 3 hours, 2 hours, depending on your system design. And contain 1 bottle of water in reservoir. So these are the functional requirement of a coffee maker system. When you want to do a failure mode effect and effect analysis, you have to partition the coffee maker as shown here in this figure. Like a coffee maker, there are brewing system and there is a electrical system. Brewing system can be divided into the filtration system, and you can look into the water reservoir subsystem and coffee pot, where coffee will get the coffee pot where coffee will be brewed. Electrical system, that's the heart, that has a switching system, PWR, clock programming, that you can program your coffee start and stop time, and water heating system to heat the water, and hot plate to keep the coffee warm. So this is a very rough example. You can divide into different way just to illustrate the how failure mode effect analysis is performed. And then you start analyzing the consequence. Let's say failure of water heating system is not working. Then I start the question, what happens if water heating subsystem is not functioning, and whether it is going to function or not. If it is has any safety consequences if it fails. If I say yes, then it has a safety and needs further detailed analysis. How heating system can be a hazard to people's health or safety, etc., or can be threat to life. If it is no, then my question is, does the failure of water heating system has impact on the coffee maker function, like coffee brewing function? And if I say no, then it has no operational consequences. But if I say I will not get my coffee, and I have operational consequences. The main purpose of coffee brewing machine is to brew the coffee, and I am not getting my coffee, so system has failed. And then you start to improve if my answer is operational, then I try to make this water heating system more robust and reliable. Reliable by using, like I say, if it is in series some circuits, I will make it into parallel configuration, etc. This is one example of the coffee making system. Now, there is a procedure for this. This is so extensively used in industry, and there are many way of approaches to this. You will find a lot of literature everywhere, but basic procedure consists of determining the item function. Like we said, what is the function of the coffee? To brew coffee and keep it at 85 degrees Celsius plus minus 5. Identifying all item failure modes. That's all critical item failure modes. Actually identify the significant items and identify their failure modes. Failure modes, you remember what we said? It's a description of the fault, how fault looks. Determining the effect of failure for each failure mode, both on component and on the overall system being analyzed. So you say if particular component fails, how it is going to affect the functionality of the particular component function, or its impact on the system as a whole. It's a purely inductive logic you are using it. Then classifying the failure by its effect on the system operation. Then I am trying to classify how critical it is, what is the impacts and all the degree of impact. Is it very severe, low, etc. Then determining the failure probability of occurrences. Of course, I would like to know what is the probability that this particular item will fail in a particular mode, because I want to know. If there is a very low probability, I should not bother much, because cost, if I want to make it 100% safe, coffee machine will be costing 1,000 times more. Identifying how the failure mode can be detected. So this is important because many times electrical circuits, etc. How can we detect the failure mode without opening everything? Some lamps, some sorts of indicators, etc. Then I know. Then identifying any design changes to eliminate the failure mode. Can we, as I said earlier, can we change the design? Can we introduce some parallel circuits, etc. so that system is not failing, component is not failing and not affecting the system. Or if it's very costly to eliminate the failure or then I should try to mitigate the impacts, the effects. Okay, even if this fails, it won't affect the function of the coffee machine. So this is in summary, very description of the procedure. And usually it is reported in like a component, let's say heating plates, function is to keep the coffee heat. Failure mode, like plate is very cold. Failure cause can be circuit is open, component level yes, system level yes, it will impact the coffee making process. So like that you can report it. So now we looked into the failure mode effect analysis, how it works. This is the method used extensively in industry. And there are different ways of doing this exercise, and most of the design engineers are aware about it. Now I'm going to introduce you to fault tree analysis. This is also very commonly used both by design engineers and also when something goes wrong or some accident takes place is used by this method is used. So let's look into that. So what is fault tree? As against failure mode effect analysis, fault tree analysis is a top-down method of analysis aimed at pinpointing the causes or combination of causes that can lead to failure. So you start looking, you assume that system has failed in design phase. Let's say I am designing something and I am telling like a coffee making machine I was taking. My coffee maker is not working. I'm not getting my coffee. Then I start looking why I'm not getting this coffee. So I'm coming from the top now, not from the bottom as I did in failure mode effect analysis. The analysis can be qualitative and quantitative. You can assign some numbers, probability values, etc. We'll be showing it how. The driving principle in FTA is how could this happen? Remember failure mode effect analysis. We ask what happens if this particular component fails, what is going to happen to the functionality of the component and functionality of the system. Here we ask event, we assume event has taken place, and then we ask how could this happen? And methodology extensively used by failures and accident investigations committee or researchers looking into causes of failures leading to system failures and accidents, etc. This is very like detective work. It's like I usually say, like if some murder has taken place and detective comes, the police comes and they start investigations looking for a alibi, etc., witness, etc. Basic fault tree symbols. And while doing fault tree analysis, we use a lot of symbols to create the tree. And like a square is a resultant event, an event which results from the combination of other events. I'll be demonstrating. Basic event, this is the core events that finishing. An event that cannot be developed any further. We don't have any clue. Dead end, we say. But these two symbols like OR gate, this is a most critical symbol that is used in fault tree analysis. The output event occurs if any of the input event occurs, like event X or event Y. Anything happens, then we'll have to use this symbol. And AND gates, like both should be important. Event 1 and event 2. The output event occurs only if all the event occurs together. And like a trapezoid is like an underdeveloped event, a primary event that represents a part of the system that is not yet fully developed. Let's look here. The relationship between fault tree analysis and reliability block diagram. You remember I said OR gate. If any event 1 takes place or event 2 takes place, system will fail. It's like a series system. If you connect to your series system lectures, it's exactly like this. If component 1 fails or component 2 fails, system will fail. Here also, if event 1 takes place or event 2 takes place, like if component 1 fails or component 2 fails, system will fail. And AND gate is like a parallel system, parallel configuration. To failure of the system, component or item 1 should fail, and also component 2 should fail. So both should fail. And this is like if I have like in house, I'm getting supply from the power station, local utilities, and I have a generator. If my generator fails and power utility fails to supply, then only I will not have electricity in my house. That's a AND gate. And like series system example, like I switch on the light I come in a darkness, switch on the light, there is no light. Either bulb has failed, then there is no light, or there is no electricity, then there will be no light. So these are the two things are related to each other and used to calculate the value of the fault tree, etc. This is one more example, like a motor fails to, electrical motor fails to operate, an illustration. Like no current to the motor or defect in the motor. There is a current, but so it is a OR gate. Like if there is a motor is failed, something has taken place, some failure, then it will not work, or there is no electricity. And then you have 4 OR events developed here, like a switch is open, there is a wiring failure, there is a fuse failure, power supply failure. That will lead to no current to the motors. Here we are further developing the fuse failure, like a fuse failure due to the overload, it got burned, or failure fuse is just open, it is not functioning. Then also there will be no supply to the motor and motor will not operate. So similarly, you do the analysis and create the, if it is a OR gate, you can create a series system configuration, and then you know the probability value of all these items, switch open, wire failure, then you can calculate the reliability. So you can start putting the numbers and you get some quantity. What is the chance that motor will fail to operate, or motor has failed, then also you can do this analysis. Summary. In system reliability evaluation methods, we looked into the reliability block diagram, and we looked into the series configuration, parallel configuration, and also we looked into the mixed configuration. Then we looked into the failure mode effect analysis. That's the method extensively used by design engineers with a driving principle. What happens if these particular components fail and how it will affect the functionality of the system. And of course, we looked also into the fault tree analysis. This is also used extensively in industry and by the in operational phase, like in accident analysis and breakdown analysis, etc. But also used in design. And here the driving principle is how could this happen? So it's a top-down event as against FM failure mode effect analysis, that is a bottom-up events. I hope you got a very brief idea how reliability predictions models and methods are used by reliability engineers. And what I have told you, I am repeating, it's a very simple, too simplified approach I have shown you. Just wanted you to have a feel how component reliability or system reliabilities are predicted and what type of models are used, how they are used, etc. Thank you.